In with the luncheon program. As I mentioned earlier, the lunch is sponsored by Space Exploration, SpaceX, and that's really a great video to watch beforehand of the whole Dragon process and docking. Representing SpaceX today is the Senior Engineer for Astronaut Safety and Mission Assurance, Garrett Reisman. Flew on STS-124, flew on STS-132, and if you have any doubts about whether the Falcon is going to be able to put people in space, Garrett will dispel them. Garrett, over to you.
Thank you very much. It's an honor to be here with you today at the AIAA convention. And it's an honor for SpaceX to be hosting this event. And it's an even bigger honor for me to introduce our keynote speaker, Michael Suffredini. Now, Michael and I have a lot in common, is going to be immediately obvious to all of you. The first is we're both very tall, handsome individuals. And we have the kind of flowing locks of hair that make us the envy of shampoo models everywhere. And it's quite annoying fending off all those requests to do advertisements. But Michael and I go way back from my days back at Johnson Space Center as an astronaut. And I could tell you that there's a great debt of gratitude I have personally for the work that Michael has done with the International Space Station program. I'll also tell you that since we're here at the AIAA, your president, Mike Griffin, did something amazing some years ago, and he started what became the Commercial Space Initiative. It was his brainchild, and what happened was this idea of leveraging the best that the private sector has to offer with the best that the government has to offer to create efficient and affordable and safe transport services to low Earth orbit was accomplished under Mike's watch. So it was the space station program run by Mike Suffredini and also his managers Alan Lindemoyer for COTS and Kathy Leaders for CRS that took this vision and implemented it. And I think we all can agree it was a tremendous success story leading to unprecedented delivery and production of a rocket and a spacecraft for money that was orders of magnitude lower than what was predicted and at a schedule that was also breathtakingly fast. It's a model I believe that is not only a great one to follow as we go forward to commercial crew, but it's a model I think that the entire federal government, when it does procurement, should look to as a way to do things better in the future. So I'd like to commend Michael's tremendous leadership of that initiative. So well done. But on a more personal level, I could tell you that as I was preparing for my first space flight back in 2007, the International Space Station had a major failure. A triple redundant computer on the Russian segment failed. All three strings came down at the same time. And the space station was in real peril because without the Russian segment, there was no way to desaturate this control moment gyros, and in fact, there was a possibility that we were going to lose this tremendous asset. And at that time, I was assigned to one of the Tiger teams to work on how to respond to this problem. And I got to see firsthand the tremendous skill with which Michael Suffredini led the effort to investigate this problem. The fact that every contingency was thought of and considered, and there was a plan for every possible future repercussion from this problem, and the level of personal effort and the personal interest he had in making sure not only that this tremendous vehicle would be safe, but that its crew would be safe, was something that was extremely obvious to me at the time. And so when I left a year later, once this problem was solved and became a crew member on the International Space Station, both myself and my crewmates, we knew one thing. We knew that Michael Suffredini had our back, and that made all the difference. So without any further ado, I'd like to introduce Mr. Michael Suffredini.
Well, good afternoon. With that kind of introduction, I think the best thing I could do is sit down and let the next thing happen, whatever it's going to be. Thank you, Garrett, very much. I'm here today to talk about Space Station and its benefits. But before I do that, I wanted to recognize both our SpaceX friends for their amazing achievement. I know the flight looked flawless, and it was about as flawless as you could hope for, but there were a number of anomalies that occurred during that mission, and it was a tribute to the engineering design of the vehicle and the operations team that successfully brought that spacecraft to station. And there's not enough words to express how impressed I was with the work those guys did as a spacecraft approached station. And I have a presentation I give that talk about challenges and anomalies we've overcome. Garrett talked about one, and a number of firsts, and this one is certainly on the list. So they deserve a great deal of respect that they have, and they've earned every bit of it. So my hat's off to you guys. Nicely done. Also, in the station world, we've designed station as we're assembling it to be able to operate. So every time we added an element, that element had to be able to stay on orbit and operate just like that, as if the next flight wasn't coming. And I thought about this because we spent about 3 years after the Columbia accident with some power ORUs that these are just the boxes on ISS that were outside. We put these elements on, but we couldn't turn them on and activate them and check them out and use them until the next elements came to orbit, which was, again, the design. But I thought about the Curiosity team guys recently, what they went through. You know, their systems are sitting, Curiosity and the Sky Crane, or sure they had some data and could see some parts of it, but they had no idea what was going to happen when they got to Mars. And so that was an amazing feat to watch, to be able to watch in large part the landing, but that they successfully brought that car-sized rover to the planet of Mars. I'm still in awe of it. So nicely done to you guys as well, and that will be recognized. So without further ado, I'll go ahead and get on with my discussion. What I wanted to do here, I know we're all very interested in exploration, what we do in Earth orbit and beyond Earth orbit, but we don't do a very good job, I don't think, of explaining the benefits of what we do. And when I talk about the benefits, I'm talking about the benefits to everyone else. I know what excites us. And I can just talk about exploration in front of you guys, and you'll be giddy by the end of the day when we talk about the advances we've made, the technologies we're already testing, the things we're going to do to explore with humans beyond low Earth orbit. But there's a whole group of taxpayers, much larger than those who understand exploration and want to do it, that don't understand why it's that important and what has it done for me lately. So today I'm going to go through that with you. At the end, I'm going to talk a little bit about station, and then I'm going to talk to you about some things that have already occurred on station that help humanity, not just for exploration. So next chart, please. Okay, clicker, hold on. Next chart, please. I'm talking to myself. Okay, Space Station, as we all know, it's an international effort, the largest peacetime effort with the largest number of countries ever attempted in recorded history. And that by itself is an amazing feat. It was built to gain knowledge, to improve life here on Earth, as well as to be a stepping stone for what I believe is humanity's destiny, and that's to travel with the stars. It's a large spacecraft. It's 100,000 pounds on orbit. It's larger than a football field. It's about the size of, 3,000-4,000 cubic foot house. Took 41 flights to build it, including the Russian flights, and 161 spacewalks. It was an amazing challenge. It had issues along the way. Garrett talked about one. We also had the U.S. computers. All three of those failed earlier in the program. We had a ripped solar array that was out of reach of the SSRMS. We've had a number of challenges, but in the end, the space station is built and operating at full capacity. By comparison, I love this chart. I show it often. Remember, stations, 15 countries. It took 10 years to build it. That was about 5 years longer than we'd planned. Without the Columbia accident, it probably would have taken us 6 or 7 anyway. So it was a difficult challenge. But when you look at unilaterally built monuments that have been built over the years, it's not unfounded to take the kind of time it took to build the spacecraft. This just shows you the steps. Mostly these were the U.S. Flights along the way that shows you the assembly steps. One of the fascinating parts of the program is what I mentioned earlier. Every time we added an element, so each one of those pictures, that spacecraft had to be designed so it could fly just like that for an extended period of time. We could not assume the next vehicle was going to show up, and that was an analytical chore and drove the design significantly. As I've talked about, it's a global effort. This picture of the world map shows you all the control centers that not only control the station, but also the logistics vehicles that support it. And of course, this is the list of logistics vehicles. Starting on the left is the shuttle that's retired. The Proton rocket, which is not used very often. It carries up large elements for our Russian colleagues, and so the next time it flies will be late 2013 when it flies up the multi-purpose logistics laboratory module, that the Russians are building. But the remainder of these are the workhorses for the ISS program. You see the SpaceX vehicle there to the right, and as we all know, last May they did their first flight. Here in October, they were supposed to be on my birthday, but they didn't quite work that out for me. They'll fly to ISS with their first CRS flight in the beginning of our long line of cargo flights, commercial cargo flights to ISS. The Antares vehicle carries the orbital Cygnus spacecraft, and I think it'll fly probably early next year. But this is what it takes to maintain a vehicle of this size and do what we're trying to do on orbit. So now the next thing is, I've got this little video for you. There's a Canadian astronaut, Chris Hadfield, who was a remarkable individual. I count him as one of my friends. He's going to fly to ISS this November, and he's going to command Increment 35 on ISS. And he explains a little bit about the potty. And I know everybody always wants to know, how does that work? And he did a fantastic job, so I thought I'd share it with you guys.
When you go to the bathroom on Earth, you're relying on gravity pretty heavily. Imagine if you were halfway done and somebody shut off gravity, it would be a mess. And you'd float off the toilet. So when we designed our space toilet, first it has to have a seat belt on it to hold you down. And then we decided to separate solids and liquids because they're easier to store that way. So we just have a tube that you pee into, and it has air pulled into the tube, so it's not a big deal. For the women, there's a cup fits up against them. For the guys, it's just like a little funnel. You just pee into this tube, and it goes into a sewage tank. But the solids that come out of your body, that's a harder problem to solve, and it's an important medical one, because on Earth, everything falls on the floor. But in space, it's going to float around. So it'll really make you sick. If you re-ingest something that came out of your body, it will really make you sick. And we can't afford to get that sick. So we designed a toilet that instead of gravity pulling everything into the toilet, it has air flow. There's air pulled down into the toilet. Sort of windy when you're sitting there, but it pulls everything out of your body. Everything that comes out of your body gets pulled down into the toilet by the air. And then in the storage tank, we just expose that to the vacuum of space. So it basically just freeze dries everything, so it kills all the bacteria so that there's no smell. And then we just store it. And then when you have a whole bunch of it stored, we put it in a little unmanned supply ship, and we undock it, and it burns up in the atmosphere. So the next time you see a beautiful shooting star going across the sky, that's what it might be.
Kind of takes the romance out of wishing on a shooting star, doesn't it? So why did we go to all this trouble? And that's really why I'm here today to talk about. So on Space Station, we separate out or categorize the type of research we do on ISS to three areas: discovery, Earth benefits, and space exploration. And why do we use Space Station? There's three main areas where ISS excels, where in fact you can't in some cases get this kind of capability. And the first, of course, is microgravity environment. As we all know, gravity is a driving force on the ground, and it affects processes and reactions so much that it's difficult to tell what other factors are playing a role and how important those factors are all the way down to the molecular level. And when you can get gravity to the point that you can eliminate it or balance it out, as we do actually on orbit, then the other factors can come into play better, and you can better understand the processes. And this is key. And being able to do this for long periods of time is very important, and that's what Station does for us. In addition, the station flies over 85% of the planet, but also, and more importantly, it covers 95% of humanity. So from the standpoint of studying the parts of the Earth that are most important to our well-being, Station is uniquely situated to do that. And finally, it's a platform for study. It's a long-term stable platform, and that has two advantages for you. One is you can study the Earth and you can study space by bringing instruments to ISS. We don't have to bring whole spacecraft to ISS, and that's a significant savings. So instead of bringing a bus that's got power and thermal and command and control and all the things you need, attitude control, instead of bringing all that to orbit, you can bring instruments to ISS, and you can observe the stars and you can observe the Earth. In addition to that, NASA is contracted with SpaceX and Orbital for enough upmass to cover the needs of the research community on board ISS. So that takes the launch cost away. So it's a really inexpensive platform to come do both Earth and space research. In addition to that, it gives us an opportunity to study how humans react during long duration travel beyond low Earth orbit. Now, it's not exactly the same. There are differences. The Earth, with the ISS circling to Earth, we get half the time we get sun, the other half we get darkness. That's not exactly true based on beta angle, but you get the idea. The radiant environment is actually lower around Earth because of the magnetic field around Earth. So there are differences, but there are enough similarities that it's an important place to do the technology development and study the human system and make sure we have ways to mitigate those effects on the population that tries to fly beyond low Earth orbit. So taking these into the three areas: discovery, AMS. As you all know, AMS is on orbit. It's been there for about 16 months now, and it is studying the origin of the universe. Pretty heady stuff. And they've been quietly collecting data. They're studying dark matter and antimatter and strangelets and all kinds of things that I don't pretend to really understand completely. But significantly is this ability to try to understand if what we believe the origins of the universe are and the theories that we have behind that are true. And so that's pretty exciting stuff. The other picture you see there is an artist's rendition of an event that was captured by an instrument on board ISS for the first time. It was actually captured also by another spacecraft called the SWIFT spacecraft in orbit. But this is what was captured was they measured the X-rays that were emanated from a black hole as it consumed a star, and that's the first time in history we've been able to actually record that. Human research and biotechnology, one of the biggest things that happens to the human body when you get on orbit is, left unmitigated, you lose about 1.5% of your bone mass per month. So if we did nothing for our astronauts in a 6-month increment, they'd lose almost 10% of their bone mass. And of course, you can imagine the significant implications. But from a studying standpoint, well, I'll back up and say, of course, the job is to mitigate that, and the team has done a remarkable job over the last several years. Our crews have come back in a very healthy state. In a couple of cases, I know they came back with more bone mass than which they launched with. So we're making great strides there. But from a research perspective, this bone loss is similar to osteoporosis that we all will eventually encounter here on Earth. And because of the speed with which it occurs, we can quickly see the mitigating effects and how well they work on a large population of crew members. And so we're making dramatic strides in that area of study as well. The physical sciences, there's Garrett for you. That's because Garrett said such a nice thing to me. I had to put his picture in my presentation. But the video there is the video that is one that's fairly famous. It's much like the flame video, but what it essentially shows you is what happens without gravity. Without gravity, you don't have convection. Without convection, when water boils or a flame burns, the heat radiates. It doesn't rise, it radiates. And so you get this interesting difference between the two events. And also what you get from that, when you boil water on the ground, because of convection and the cold replacing the hot and hot rising, the water essentially gets stirred. On orbit, you end up with these big temperature gradients, and these all play a role in the study of fluids for future applications. Exploration. We all understand it. We're all trying to decide exactly where we want to go next. But basically, we're going to have to do the kind of research to show ourselves that we have the technologies we need, and then we need to build these systems, and we need to test these systems in low Earth orbit before we decide we're going to put our humans' lives on the line to rely on them. And so that's part of what's going on Space Station today. We're doing materials testing. Again, that applies to a lot of aspects, not only exploration. The picture of the ECLS system you see there is the regenerative system. Today on ISS, we take urine and condensate and we turn it into potable water. So the objective over time is to evolve these systems, make them highly reliable, and then utilize these systems beyond low Earth orbit. Another one on there is the SCAN testbed. That's a software-defined radio. Also, it's going to have huge applications for exploration. Earth benefits. Earth benefits are in, we have it in 3 themes, we call them: human health, Earth observation, and disaster response and education. And the reason why I'm here today is to go through these next few charts with you and show you what's going on today that really is a benefit to us all, not just to help us get beyond low Earth orbit, but to help us live here on this planet. The first one I'll talk about is salmonella. Salmonella affects millions of people around the world, and in impoverished nations, it has a very high death rate, particularly of children. So in studying, doing research on board orbit, they found a gene in the salmonella bacteria that was sensitive to microgravity, and in fact, it became more virulent. And with this information, they figured out a way to make it, to attack the bacteria by affecting this gene. And they're getting ready to go into trials on a vaccine for salmonella. And so that'll have a big effect on our lives and many people's lives. In addition, at the very end there, they talk about methicillin-resistant Staphylococcus aureus. This is the superbug you hear of in hospitals. It affects over 1 million people in this country alone and kills more people than AIDS does. And this same technique they used on the salmonella bacteria, they think will have the same effect on MRSA, and they're starting that effort today on board ISS. Cancer treatment. course, this is very important to all of us. This was work they've done on station looking at surface tension and creating modules that we now replicate on the ground. And these modules have the surface tension such that they don't get dissolved by the bloodstream. They get dissolved when they meet the tumor that they're intended to attack. And so what this allows you to do is treat more effectively the tumors without killing the human body. Today, the treatments attack the whole body. This will allow us to treat just the specific tumor itself. And you can imagine the effects that'll have if any of you, and many of us have been touched by family members and friends who've had cancer. It's watching the effect it has on the body while they're trying to fight the cancer is tragic. And it's a double hit because you make the body weaker, and the body needs its strength to fight the tumor as well. And so this gives you both of those. It gives you ability to treat the tumor while keeping the rest of the body healthy. It's an amazing accomplishment. Let's see, disaster relief. This is a picture in Pakistan, but this same application has occurred in Iran and Iraq and Haiti and several other places in the world today. There's a filter we have in our water processor that has a resin in it, and it's impregnated with iodine. And these blue filters you see hanging up there are just that. And you pour water into it from almost any source, and what you get out of it is drinkable water. And it requires no power. So if you have gravity-fed water source, you can supply potable water to communities. And so this is an outgrowth of the regenerative ecosystem that we built for Space Station. Nutrition, bone loss, again, I'll talk just a skosh about it, but we're finding on orbit the dietary effects that are associated with bone loss. It's really more than just the bone. You have neurological effects, degradation on orbit. All these things affect the health of the body, and so we've learned a lot. One of the ones that are talked about most, and you may have heard your physician mention to you now, is vitamin D. We do not get enough vitamin D, generally speaking, because we spend more and more time indoors. Of course, on station, we spend 6 months indoors, and so it's and its effect on the crew's health was noticed on board ISS, and it's now become a standard question as part of your physical. So if you haven't heard it yet, when your doctor brings it up, you'll know it kind of got kicked off by studies of humans on board. Materials. This is going to be fascinating for us in the years to come. We're studying materials and the act in a microgravity environment when we melt alloys or any material and gravity is no longer affected, it comes back together at a molecular level in a different way, generally in a way that's stronger. And there's been several of these experiments done on orbit today that have application on the ground. There's a very exciting one they haven't published any results, but where a aluminum titanium alloy was melted and cooled, and the result was a material that was twice as strong, actually 4 times as strong. So essentially what you can do is go build things at half the mass and twice the strength based on this research alone. So these kinds of things will affect you immediately. This particular application has been talked about in terms of turbine blades, but you can imagine the implications across a wide range. Earth observation. So this particular volcano erupted in the Kuril Islands, which is north of Japan and just south of the Kamchatka Peninsula of Russia. This was noticed by the crew on board ISS in 2009 when it erupted. It was first noted by the crew and reported down, and I'm sure it was noted by the inhabitants of the islands, but they weren't calling anybody. But we alerted the FAA, and they rerouted traffic as a result of that. Now, that's not to say that what you do on ISS is put a crew's nose to the window and say, tell me what you see all the time. And they do spend a lot of time looking out the window. But really, the point is there's a platform up there where instruments can be mounted relatively easy and look for these kinds of things. Hyperspectral imaging is probably one of the more exciting areas. This particular application was studying columns of water along coastal areas, and you can tell depths and you can tell the constituents of the water, and they were looking for the surface, how the surface came up to the shore, but also they were studying what was in the water from a contamination standpoint. But these type of imagers, depending on the kind you fly and the frequencies used, these types of imagers can be used for agriculture and oil and gas and have a number of applications. So this is the first instrument on ISS. I bet we've had discussions or having discussions about 3 other entities who want to try to put more imagers on ISS. So I'm looking forward to that. Finally, reaching out to our students, and this to me is the most important thing we do. Today, about 31 million students have been in contact with the crew or done research on board ISS. It talks about, this chart talks about the ham radio ability of a cruise for the students to put together questions and talk directly to crews for short periods of time. Also, EarthCam that was kicked off by the late Sally Ride is an opportunity to have the students decide what images they want of the Earth, and then we set up a timeline by which we'll fly over that, and then the students get the data and use that data. Also, one of the other things we're doing that I'm most proud of, I think, is a program where we have students. Today we have 37 schools across 15 states, mostly high schools, that build hardware for us. Most of the hardware is training hardware. Some pieces of flight hardware has been built by them, but we teach we teach the kids so much about space, what it takes to design hardware for space, the attention to detail, what's important, what's not important, and these kids take this in sort of an energized way and go off to college to become engineers to fly in space or do the next great thing for us all. So to me, this is a very important part of what we do for a space station. At this point, I want to leave you with a video. This video tries to answer the question, why do we dare to take the challenge of space exploration? It was put together by a group of folks over at the Johnson Space Center that work in the space station program and also in the Orion program. So enjoy. When this is over with, I'll be happy to take questions.
We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic flight of fantasy became reality. Then, a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space. We have always looked up. For centuries, we wondered what was on the other side of the sky, and we have begun to answer that question. We have learned that all the exploration humankind has achieved is only a beginning. Right now, men and women are working on the next steps to go farther than we have ever gone before. New vessels will carry us, and new destinations await us. Everything we have ever accomplished leads to this moment in time, where exploration will now take us to the planets and the stars. Our nearest neighbors in the night sky have beckoned us, invited us, dared us to reach for them. We are the explorers. Throughout our history, we have taken both small steps and giant leaps in that pursuit. Our next destination awaits. We don't know what new discoveries lie ahead, but this is the very reason we must go.
Questions?
We have time for a couple questions if there's anyone who wants to go to the microphone there. And we also have a whole bunch of program to go. This may be a question coming up or not.
It's a long trip, but
Yep, there you go.
Is there any chance, even at this late date, that a centrifuge, a human-sized centrifuge, might be added to the International Space Station, whether rigid, inflatable, tethered, so that we can find out what partial gravity, such as moon-level gravity and Mars-level gravity, affects on human biology?
you know, that was, we had a very large centrifuge in the program for some time that basically, due to the research needs, eventually was canceled. However, we fly smaller centrifuges today. We expect to pick up our work with mice, and I would expect that over time that centrifuges will be necessary for those as well. But very large centrifuges I haven't heard people talk about. But we're always willing to accommodate whatever.
What is the long-term potential for space station beyond 2020?
Say that again.
The long-term potential for space station beyond 2020?
We are studying to extend ISS to 2020. We went ahead and worked it to 2028 because that's 30 years on the oldest module. So that's what we're studying. Today I have not seen anything that tells me we can't go to 2028. So the system can go that long. So part of the reason why I am talking to you today about the benefits beyond just the space-related benefits is in hopes that you will do the same thing when your neighbor asks you why we're spending $60 to $100 billion on a space station, and you explain that it's more than just for exploration. It actually has very real effects for us here on the ground. It's that kind of conversation that's got to happen for us to decide to keep it beyond 2020. But the station system will be able to operate at least to 2028, in my opinion.
Following up on that, leaving out overhead, so what's the split between the money spent on ISS research that has pretty direct benefits versus more pure science or exploration or something?
You know, I don't know the answer to that question. That is a difficult question to answer because what you're trying to do is predict things that have occurred or will occur. Medical research is one. It takes about 10 years from the time you learn something at a research level, which is what you get on ISS, to the time you have a drug. And then you have to predict what you gain from that. And so I haven't seen any data that answers that question, although I wish I could. I'll take an action. Get some guys to work on that. Maybe we can answer it next time. All right. Well, look, thank you guys very much. I appreciate your attention.
Mike, thank you so much. And you know, Mike showed us an awful lot of almost factoids about the station and the role it plays and for helping a lot of things. Take those with you. Take some of them with you, because we constantly get asked, so what? Why are we doing this? We have answers. We have things we can answer, and take that with you and help us make sure the public understands how important that amazing facility really is. Well, before we move on to the technical session, we have a real treat to finish the luncheon program. Is there anybody in this room that didn't watch either in the live or the next morning the Curiosity? I dare you to raise your hand if you didn't. Yeah, I knew. And anybody in the room that hasn't watched it at least twice? Yeah. An amazing, amazing event. And one of the interesting things that was pointed out was that the American public wasn't captured by the 7 minutes of terror. They were captured by the men and women that were on that screen and the emotion they showed and the skill and the discipline and all that went with that. We are very proud today and very pleased to have, I won't say the team. Pete would be angry with me if I said the team. I will tell you we have 17 people who are involved in that, and Pete will later on tell you probably more about that. But if all of you wearing the blue shirts that are on the Curiosity, part of the Curiosity team, would you stand up and let us give you a round of applause? And just in case you haven't seen it enough times, we have a video that captures more of that. So if you'd roll the video, please, on Curiosity. My wife and I were up at 1:30 in the morning.
Looking good. Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for backshell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Time to see where our curiosity will take us.
Got thumbnails.
A whole bunch of men and women, most of them engineers, acting like a bunch of damn kids, and they deserved every bit of it. One more time. You know, Pete Theisinger will tell you that it was a giant group that made this happen, but there was a guy in charge, and Pete Theisinger was that guy. I won't say that he's got Mars stamped all over him, because he's been doing JPL stuff since 1967. And if you read really carefully into the bio, you find that he was involved with Galileo, and he was involved with Voyager, and he was involved with Mariner, and then he was involved with this and to Mars, and that to Mars, and another to Mars, and then there was a rover a few years ago to Mars, and another rover to Mars. And Curiosity, this guy has done Mars. He's put things on Mars that no human being could believe it could be done. You want to see that team? They're on the cover of Aerospace America, but you get to see Pete real live right now. Pete?
Richard Cook, my deputy and at various times a deputy and project manager on Spirit and Opportunity as well, said on the night at the press conference that never gets old, and he's right, it never gets old. I've watched that video probably 10 times, and every time you see it, even though it happened 40 days ago and you know it's really landed safely, your heart kind of goes, really? I'd like to introduce you to the people who stood up, to put a name to the face. With us today are Howard Eisen and Richard Kornfeld and Jeff Umlin and Paul Hardy and myself, Tracy Nielsen and George Richdale, Arisa Hines, Ben Cece, Jeff Simmons, Steve Collins, Rich Rainin, Art Thompson, Richard Brace, Arthur Amador, Richard Cook, Shivali Reddy, Adam Stelzner. And they are only a small part of the thousands and thousands of people that helped accomplish that over the last 7 or 8 years. There were contributions, major contributions from members of the NASA family, Kennedy, Ames, Langley, Goddard. I'm probably forgetting one, and I'll get killed later. Department of Energy supplied the RTG for us, and we had foreign partnerships, both equipment and instruments provided by Canada and Germany and Spain and Russia. A tremendous effort by a large number of people to cause this to happen. And although some of us are fortunate enough to be the face of it all, the reality is that it was a very large group of people in tremendous teamwork that accomplished this result. Fortunately, this is the gift that keeps on giving. The mission is really 2 years in the future as we move forward from here. As I like to point out to people every once in a while, I thank you for the applause, but we have accomplished 2 of the level 1 requirements, which was launch out of Kennedy, land on Mars. We've got a few more yet to go. And we're going to see great science in the future. It'll be engaging to the public, I think, in the way that you saw what we saw at the various sites, but also, and more importantly, and mentioned earlier, in terms of the effect of the youth of this country, the real payoff of this is not only in the science, it's not only on the technology pool that we engage in, but most of all, it's in the engagement of the youth of this country. We know that we have a crisis of technical education in this country. If we're to be globally competitive, we must be able to have that crisis reversed. And events like this, events like the space station, everything that NASA does, impel the youth to get interested in technical education. Excuse me. And maybe not apply it to space, maybe apply it on Earth, maybe apply it in information or bio disciplines. But that's where the payoff for this is. Thank you very much for the team, and we'll be playing this song for a couple of years.
Well, what a great year. Start with Dragon and with Curiosity, and the reminder that all he did was launch and land. Now they get to do the science, and that's going to be exciting as well. Thanks again to SpaceX for sponsoring this luncheon. Thanks again to SpaceX for putting Dragon on station. Heck of a good job, Garrett. Sure appreciate it. Right over there, coffee and dessert. Next session starts at 2 o'clock. Thanks for coming to Space 2012.